Back in 2019 at their Worldwide Developer Conference, Apple announced they were making some drastic changes to the way they were going to handle the kernel space in their Mac operating system. Today I'm going to go over one of those results of that change, the Endpoint Security Framework. Today we'll be covering what exactly the Endpoint Security Framework, or ESF, is, why it's important from the detection and security industry, some of the issues that I encountered with its use during my initial experimentation, my devised POC solution, which I codenamed ESFang, and I'll briefly go over a use case against the Meterpreter agent against how the telemetry can be used for detection purposes. So first of all, what exactly is the Endpoint Security Framework? So the Endpoint Security Framework is a macOS component devised by Apple for security needs specifically. It works at the kernel level and in many ways works very similar to ETW on Windows or event tracing for Windows. It works allowing for real-time event telemetry acquisition, which allows for proactive instead of purely reactive defense. And it's a successor to the OpenBSM in many ways. OpenBSM is the Open Basic Security Module developed by Sun Systems, which was used previously for many auditing purposes. What does this look like in general? The image on the right gives you a very high-level overview of how this works. So the blue sections at the bottom represent the user space. So the endpoint security application will subscribe to the kernel space in order to collect telemetry or event types, which are specific to whatever detection purposes you want to do. Now, the messages from the kernel space will then be piped back to the user space to your application to be run through your detection stack for detection purposes. In the bottom left is an example of one of the event outputs. It has multiple detection criteria, lots of different data points in every single event type. These can include things like environmental variables, user ID, PPID, parent process ID, and even things like CD hash for whether the binary has been signed by a developer. But why is Endpoint Security Framework important to us? So, due to the announcement made by Apple back in 2019, they were deprecating something called KEX, or kernel extensions from third-party vendors. What this means is that they were removing the access from third-party vendors to install their own kernel extensions. Primarily before this, security vendors would install a kernel extension in order to hook into the telemetry they wanted to monitor, and then output that to the detection stack for detection purposes. But by removing or deprecating KEX, they had to introduce something else. To this, Apple introduced something called system extensions. System extensions is Apple's solution to the deprecation of kernel extensions by providing a managed way that Apple maintains and develops for user space to access the kernel space for this telemetry acquisition. However, it is controlled by Apple's development team instead of allowing ad hoc third-party access to the kernel itself. One of the primary benefits to ESF is that it is very easy to integrate. Apple has put a lot of time into making this very simple to integrate into your detection stack. And it's much simpler than OpenBSM, which was very clunky and difficult to use. And there's multiple papers on the problems with OpenBSM. So it is something worth looking into just to see the numerous issues that were with that system and how ESF has solved a lot of them. So I'll quickly go over the old way of how monitoring worked. So as you can see, you had the user space at the bottom and the kernel space at the top with logs being generated in the background. As I said, third-party vendors would install a kernel extension in the kernel space, and their monitoring program would hook into or call to that kernel extension in order to generate telemetry and run through the detection stack. OpenBSM works by hooking different log files, and then when the log file would be populated, the data will be piped through the hooks back to the detection system, again for further auditing. The new way is very different. So the system extension works in the user space. There are 3 specific frameworks that were developed due to Apple deprecating KEX: the Network Extension Framework, Endpoint Security Framework, ESF where we're looking, and the Driver Kit Framework. Now, by using all of these, you have a very detailed view of the low-level activity of a system, but we're going to focus on Endpoint Security Framework here. And by accessing the system extension for ESF, you then access the kernel extension for ESF, which allows for that limited and constrained version of kernel access developed by Apple. But why did they make that change in the first place? Why did they remove the access to the kernel? The main reason they said is for stability and for security. Now, because third-party vendors to the kernel or third-party access to kernel space in general has security problems, Apple's removal of third-party access eliminates that almost entirely. It also increases the stability of the system, preventing black screens of death, or BSODs. This normally occurs where third-party vendors have made inaccurate memory allocations, which can cause the system to crash, which in Windows we call blue screens of death. One of the other parts is that although kernel extensions have been deprecated, you can still use them in modern Mac systems, but you have to severely degrade the security profile of the system. Whereas beforehand, you used to be able to run kernel or install kernel extensions ad hoc, now you have to deliberately reduce the security settings of the system, reboot the system in order to install them, which makes it very difficult, and it's only done really for development purposes. But what were some of the issues with the Endpoint Security Framework during my experimentation? So when I initially started experimenting with ESF back in mid-2020, three particular issues stood out to me. One of them was a bottlenecking issue. The second is system verbosity. And the last is a real parent process ID issue related to the PPID of running processes. So the bottlenecking issue was originally found when I was looking at available researchers who had made existing PSCs back in the early 2020. And there were some vendor solutions as well. But by running the same experiment identically on the same system, you would get a different subset of results, even though you were conducting the same activity. Some data points would be lost, some would be added, depending on how you're running that activity, how you're running the ESF collector. And it made no sense. There was no consistency in why this was happening. And I spent several weeks, about a month or two actually, trying to figure out exactly why this was occurring, because there was no real indicator of why this memory was being inconsistent. During further analysis, it actually turned out that the problem was actually in the kernel level itself. It's not a flaw, it's a limitation in how the kernel queue system works for the messages that are sent from the kernel space to the user space. Namely, what was happening was when you subscribe a user client to an event type in the kernel space, it populates a queue in the kernel space, and then it issues them back to the user space for ingestion. But what was happening was that this queue in the kernel space was being overloaded. And because of this, data packets or data events were being silently dropped on the kernel level without an indicator to the user space, meaning you got a lack of data or inconsistent data without being alerted that this was happening, which is very frustrating. Two potential solutions presented themselves. One is a multi-client system, and the second is event muting. I'll go over event muting first, because this is the solution that Apple have provided as part of the framework. Event muting works on the kernel side, so when your client subscribes to particular data or event types you want to see, you can also put in additional filters. This is normally done by process file locations or process tokens. The problem with event muting is it's not fine-tunable enough currently. It's more a sort of sledgehammer approach, so you can either block everything or not enough. So when I was looking at the viable solutions, although Apple have introduced this, it's just not accurate enough currently to make this a viable option. The multi-client system, however, was far more appropriate. So within a endpoint security application, you have a client object which, as I said, subscribes to event types in the kernel space. But instead of having just one object, if you have multiple endpoint security objects within the same application, subscribe to a subset of event types you want, they each get their own kernel queue, which prevents the overload. So each client will have its own queue in kernel space, and if you have them as reduced event numbers being monitored, you don't get that overload, and you can conglomerate them in the user space side itself. One thing to note is that between macOS 10.15 Catalina, when the Endpoint Security Framework was introduced, and 10.15.4, the system software development kit that was available was suddenly updated to include something called secnum, or sequence number, inside the message object that was returned from the kernel space. The value of this is that although on the kernel side it doesn't indicate whether a dropping of data has occurred, by analyzing the sequence number in the messages, you can see if there are gaps. And through this method, although it's still not going to alert you, you can monitor for it, and then you can do dynamic rebalancing if necessary in order to make sure you're not getting that overload, which was a nice solution. System verbosity, so I'll just explain this side. So the two red boxes you can see are origin UID, or the user ID from where this event was coming from, with an ID of 0. So this is actually the system ID of the running system. And what was happening is when you look at ESF telemetry that's acquired, there's a lot of system activity. Because it works at the kernel level, it also picks up all the system daemons and all the drivers, managing systems, and all their activity as well, which can create a lot of bloat in the data that you're acquiring, which, as you can imagine, makes filtering very difficult because you get this massive amount of data that has to be handled and throughput and up-filtered and all these sort of things. So you either have a choice, again, like with the previous problem, where you can either filter before or after collection. To filter before, you have to use event muting, because it's the only way to put filtering on the kernel side. Event muting, however, as I said, it's too much of a sledgehammer and it's too general, so you either have to completely omit system-level processes in general, or you have to omit individual process instances, which are far too specific. So it can lead to basically blocking out all system-level activity, which, if the system user is compromised on an endpoint, can lead to ignorance of that compromise, which in itself is dangerous. The client-side filtering, because you have to allow the data to come through, which, as we've said, can be extremely verbose, you might end up with a bottlenecking issue anyway, simply because the input is so large. However, using the previous solutions by doing multi-side clients, you could kind of sidestep that issue, but it's not necessarily guaranteed, and you're going to have to rebalance that as you go. The parent process ID, so again, this is a long-running problem in Mac systems, and the reason is because of how cross-process communication works on the Mac operating system. Primarily, what's happening here is at the bottom, there's launchd being launched by launchd, which in turn is actually running XPC proxy. Now, these components are how Apple has dictated that one process will communicate with another, and it normally goes through one of these programs. But if you're looking at the process chain of what program spawned one other program, if you've got XPC proxy or launchd in the middle, it can make following that back quite difficult, especially if it runs at the system level. And it has a process ID of 1, which is extremely verbose across the system because it is a system-level management cross-process communication system. So tracing that becomes very problematic. At the top, you can actually see a real PPID identifier, which actually has the correct PPID for this process. But this was using a solution which was devised by Patrick Wardle, which was launchd XPC, which was able to backtrace through some underlying data in order to find that solution. But you end up with this solution where even when the solutions that were there before are not future-proof. So since then, Apple have introduced something called Running Board, which is another version of launchd and XPC proxy, which has actually made the previous solutions unviable because it could also run through this additional feature, which means that you end up in a situation where you have all these processes running and not an accurate way to backtrace them through a system, which is very frustrating. As I just mentioned, there is no future-proofing. The reason for this is that each Mac OS that they release, they could potentially add more XPC features to their systems, which they have done in the past and have made previous solutions such as TrueTree by Jaron Bradley and Launch XPC by Patrick Wardle, as I just mentioned, unfortunately obsolete. The reason is that these adjustments happen so low in the system, and they can be so different between one version and the next, that creating anything that persists over multiple versions, very, very difficult. In the POC that I developed, I actually used launch.dxpc, and as I mentioned before, this does not account for the XPC process running board, which is a limitation on the POC. So going over my solution, which I codenamed ESFang, this was heavily based on the work by Patrick Wardle, Chris Ross, and Omar Ikram back in late 2019 when Catalina was available. They did a lot of the groundwork in how ESF could be taken from and how the ESF clients worked. And they really paved the way for ESF telemetry acquisition. And a lot of the POC was taken and adapted from their prior work. I developed ESFang early in 2021. It is now available for public consumption on the Countercept GitHub. It allows for dynamic ingestion of 52 different event types. These span from process events, file metadata events, inter-process connection port allocations and things like that. But the main difference between what was available before and this particular solution is that each time you run it, you can specify which events you want to ingest. So the prior solutions would say file monitoring solution, but it would ingest all of the file monitoring events, which should be file create, file write, anything to that effect. And because of that, you ended up potentially with the bottleneck issue that I mentioned before. But by being able to do a case-by-case dynamic event specification, you can sidestep that by only looking for the event types that you want. Going by the multi-client solution, this POC is only a single run. I'd never coded in Objective-C before, but adapting the POC to be a multi-threaded system would allow you to put in that multi-client system as part of it as a standalone ingestion. It has JSON output specifically so that it has easy upstream design into available databases to be run through additional detection stacks. So I'm now going to briefly go over a use case against the Meterpreter agent. This was done against the macOS system 11.2.2, and I used my ESFang POC in order to collect the telemetry. This was only done against the agent and the Meterpreter agent. It was not done against Metasploit's payload capabilities, which are available to it. It was only based on the agent's capabilities alone. I did not focus on how the agent got onto the system originally. I'm only focused on post-exploitation. So once the agent is on a host, if it conducts activity, what can ESF potentially monitor for? And this was only done on a single host, so it's not representative of an enterprise environment where it could do lateral movement or it could potentially do credential stealing and move that way. This is a quite squished graph. This is an overall findings. So this is a representation of all of the event types that were available and ingested and how they were seen for different activities. Now you can see that some of them, like webcam stream, which is not operational secure, is extremely verbose, so it had multiple events generated for it, whereas some of these smaller ones, like edit file, you can there is a bar there, but you can't even see it, it's so small. But what this wants to represent is that depending on the activity that's being conducted, you can get a lot or even very small amounts of information, but the information that's generated can be extremely valuable for detection purposes. So if we look at the installation for the Meterpreter agent, you can see that there's a number of key event types that were conducted. Two of which that stand out very high are mprotect or memory protect and read directory. Now, although these stand out as being quite high and verbose, they're actually not that valuable. The reason for this is when you drill down into them, any application that's executed will conduct a number of memory protect operations because all the sections that it's loading into memory will have different protection levels assigned to them. So although this is quite high, it's not necessarily easy to identify malicious activity. Read directory equally, a lot of the temporary or etc directories that are used for system information when applications are loaded, it's quite generic and it's not necessarily specific and easy to identify. However, when we look down at open or FCNTL or file control, things get a bit more interesting. So when you look at the activity that was being conducted by the Meterpreter agent, the files that it opened were very specific. So when you start to drill down into that data and start to create detection profiles, these two event types cross-referenced allow you to create a detection profile specifically for the Meterpreter agent, which is very valuable. So if we break down that graph into an overview, it had 259 data points, but quantity is not an indicator of quality. As we know from detection, if you have too much, it can just swamp you and you become blind to other things. But equally, if you have enough data points and you have enough processing power under it, you can do enough cross-referencing in order to make very accurate or very high-fidelity detection profiles. So let's look at some of the more valuable data events that are available within the ESF itself. So notify open is a file event. So this is anytime a file is opened, this event type will be generated and it will specify what process accessed what file at what time. Now, if you look at installation, the 30 open events that I mentioned before are extremely valuable in patterning when the Meterpreter agent is deployed. However, again, you look all the way to the right at the non-OPSEC or operational secure webcam streaming, we're at 478. Now, if you look at the files that it was accessing with that, it's the same file over and over again, which is very abnormal because the file is related to webcam access. So it's very easy to profile, but attackers are they will very unlikely to use that particular action. However, process list was one that stood out as very interesting. The reason for that is every process that was running, the agent opened an individual file related to the process it was enumerating. So instead of using something like an internal process enumeration command, it was using a file opening enumeration on the Mac system, which allowed you to pattern by saying, if one process is opening files related to every other process, you can see that as anomalous. Notify write, this is again another file operation, so this is writing to any existing file. As you can imagine, edit file down there on the left had one lonely event. That's to be expected, so in both cases, it was writing the same amount of data to a target file. However, edit file only had one event, but upload had 226 events. Now, this was particularly interesting because the notify write allows you to see how much data was being written to the file. Now, in edit file, it was the whole data block being written in one event, and it specified the correct size. However, upload, it had a much smaller write size. And the reason for this is that each packet that the agent received from its controller, it was appending to the target file one packet at a time, which allowed 226 events to be generated. So again, if you start to pattern behavior by is a binary uploading very small packets to the same file over and over and over again in quick succession, you can start to identify this sort of activity on a system. Lastly, we'll look at IOKit. So IOKit, or input-output, is done for hardware or driver access on the Mac system. And as you can see from webcam streaming, again, not OPSEC, so 220 events, but equally it did the same for screen share. So where it's hijacking the display input-output, it's able to, you can see the events when this occurs, which are very, very abnormal. You don't see a lot of IOKit information events being generated by non-system binaries. So if you filter out UID 0 with IOKit open, you can start to identify some low-level or potentially abnormal behavior. This is an overview of the full list of value types. This was based off of investigations done over multiple attack frameworks, such as Merlin or Mac Shell Swift, Sliver, all of those sort of frameworks. One of the ones that really stood out for me was PTY Grant, particularly. So that is pseudo-terminal generation. So a lot of interactive user shells that are generated by agents normally just pipe the output directly from a generated bash terminal, and then they just filter it back through the agent. But for Mac Shell Swift, they use a pseudo-terminal instead, which creates a master-slave association between two files, which allows them to pipe commands to a pseudo-terminal and then filter them back that way. So if you were filtering for a bash instance, as you would typically expect, you wouldn't necessarily detect it, which was quite interesting. So in summary, over the ESF, it is an extremely powerful and readily updated component of macOS systems. This is something that Apple are clearly taking their time to improve, and it's something that they are readily involving themselves in order to improve detection capabilities for security vendors on their system. Because of the removal of, or the deprecation of kernel access, its use is no longer going to be optional. Moving forward, if you want to have this low-level telemetry, you're going to have to use Endpoint Security Framework. So we're going to have to get used to the way that Apple's doing it and equally involve ourselves in the development process and notifying them of issues when they occur. As we said, back at the original 10.15 SDK or development kits, there were some issues, some of which I've identified today. There are additional ones that are constantly being found, but they are being addressed, which is really positive to see. Compared to prior solutions, so developing your own kernel extension using the clunky old OpenBSM, ESF is very easy. Coding it is very simple to do, and equally, its ingestion of data and putting it into a format that better suits your data requirements is relatively simple. It allows for high detection. As I said from the use case, although I briefly overlooked it, did an overview, the capability of the data output from that sort of low-level information allows for really high-fidelity detections. But unfortunately, because of some of the issues mentioned before, filtering either on the kernel or the application side itself is essential, simply because there's just so much data to go through. So unless you have the capability to filter, to acquire all that data in upstream, filtering per endpoint is going to be required.